Thank you very much for the invitation. I very recently learned that this should be an introductory talk, so please ask questions at any point. And I decided to make a quite long introduction to toric varieties as they will be used. So toric varieties were already mentioned, and toric varieties that I will use will come in two settings, affine and projective. And the definition, even if you know toric varieties, it will be slightly maybe different than the one you know, because for me, a toric variety will be given as the closure of an image of a map Okay, so this is a torus, and this is what I call an algebraic torus, n-dimensional and m-dimensional. When I will be considering maps between algebraic tori, I mean, first of all, that this is an algebraic map, and second of all, that it preserves the group of the torus. So this is a group with multiplication coordinate-wise, and there are not many maps that preserve the torus structure. Namely, they all have to be given by Laurent monomials. This is an easy proof. So in fact, such a map has to be given. Let's say that the coordinates here are x. So I will write it like this. And here I'm using a multi-index notation. This is by definition x1 to a1 1 times xn to a1n, and ai's are in z to the n. So I'm using a multi-index notation. Yeah? This is a map of tori, and the image of a tori will be a torus. This is not yet interesting. Any questions? Maybe here, is it visible? Yeah. And the interesting thing is when we look at this torus somewhere. So let's start with an affine space. And an affine toric variety for me, so a definition, an affine toric variety is just the closure of the image of f inside the affine space, the m-dimensional affine space. That's a definition of an affine toric variety. And a few remarks. Such an image does not have to be closed, does not have to be normal. And an example is if we go from C to C2, well, I just need to specify two monomials. So let us take t squared t to the third. Now, what is the image? Well, the image is given by the equation x to the third minus y squared. It's a curve known as the cusp. So it's a singular curve. 0 is a singular point. In particular, this curve is non-smooth, and curve non-smooth means it's not normal, because normal varieties are smooth in codimension 1, and this is one-dimensional. But for me, it is a toric variety, an affine toric variety. How do we represent affine toric varieties? The idea, in fact, goes back to Newton, and the idea is, instead of remembering these monomial maps and the geometric picture, we just need to remember the exponents. So we will be identifying affine toric varieties with subsets of lattice points. And this goes both ways. If we have an affine toric variety, we can find the corresponding subset of lattice points. But if someone gives you any subset of lattice points, it gives you a toric variety with an equivariant toric embedding in an affine space. And the principal idea of toric geometry is that all of the geometric properties of this affine toric variety are in fact encoded by the simple geometry or combinatorics of lattice points in a lattice. If you would like to understand it in a slightly more advanced setting, what are these things? These are characters of a torus, which means maps from an n-dimensional torus to C star that preserve the group action. This is the lattice of characters. There is an intrinsic operation of addition on characters coming from the group action on C star. And here we are just choosing m characters in a lattice of characters of a torus. So these are affine toric varieties, and now in the same way I'm going to introduce projective toric varieties, and basically nothing changes apart from the fact that I will map to the torus in PM. Well, if I go from C star, we can make it like a map. Yes, so just as before, I was mapping to the torus of AM. Note that here the image will also be in the torus. And what's the torus in the projective space? If you fix the coordinates, there is a torus, also m-dimensional, of all coordinates not equal to 0. Yeah, that's also a torus. The image will be in the torus, and we again take the closure of the image. So just the same, affine and now projective. Toric variety is the closure of an image of F. And again, we could say that we represent them as points in the lattice, but there is a better way to do it, because note that we would get the same map if we took a product with C star, and if we call this coordinate t, we can multiply this by t. And because we are going to the projective space, we didn't change anything. Yeah? So it is better to remember that all of those exponents really have another exponent starting with 1. So instead of looking at a0 and am in the lattice z to the n, we put it usually at height 1. I'm making here a very combinatorial picture inside a lattice 1 bigger. Yes? So I'm adding a new coordinate, and I'm putting my characters at height 1. Just sort of to remember that my variety is projective. But coming back, if I have points in a lattice, I obtain an affine toric variety. So maybe a first question to the audience: what's the relation between looking at these points as a projective toric variety and as an affine toric variety? What's the relation between these two varieties? Are they related anyhow, in somehow? So what's the difference? I mean, once we take a map to a projective space, and once we take a map to an affine space. And both of the times we take the closure of the image. And the map is of this form. There is like t times x to something, t times x to something, and this t is because we are looking at those points. Yeah, so what's the difference between a map to a projective space and to an affine space of this form? Yeah, so if here we have an image x, yeah, in PM, so first of all, now we have m plus 1 points. So there will be some other variety in A, m plus 1. And what it will be, how it's related to x. Yes, yes, I think it was correct answer. Affine cone, yes, it's just an affine cone. Okay. Now, so I would like you to keep this in mind that that we have two types of varieties, but there is not even one. There are many more affine varieties floating around here. Well, what's the idea between these other affine varieties? Well, we have to recall that the projective space is really covered by affine spaces. How do you understand a projective variety or a projective space? Well, by definition, it's a gluing of an affine space. Yes, so there are these affine spaces AM that are given by the condition that yi is, let's say, non-zero, or yi is equal to 1. Let's call it ith affine piece. And now you can look at the intersection of x with ai. This is certainly an affine variety, and it's also a toric affine variety. And if it's an affine toric variety, it needs to correspond to some characters. And what's the idea here? Well, here we distinguished a coordinate. Yes, we distinguished a coordinate, so it means we chose one monomial among those. And we set it equal to 1. So the question is, can we somehow, from the one hand, change this map, and from the other hand, not change the image in such a way that there is a 1 on ith coordinate? Well, there is a usual trick. You divide by the ith monomial. Yes? So what will you get if you do this? You will get a 1 here, but those other things, they will change. You will get an x0 minus ai, xam minus ai. Yes? So I really didn't change the map. I just changed its representation. Yes? So this variety, it will correspond to a set a0 minus ai, am minus ai. Okay, so all of this, I said so far, works for non-normal varieties. And in particular, one of the very strong tools of toric geometry is a relation among the equations defining an affine or a projective toric variety and linear integral relations among lattice points. And I don't want to maybe go very much into details due to time restrictions, but the thing is that if you have two lattice points, let's make them yellow, we look for integral relations among them. So in other words, we want 2 times some integer plus 3 times some integer equal to 0. Well, if you take a second, you will see that there is this relation. 3 times 2, well, let's put it minus. Minus 2 times 3 is equal to 0. And this is exactly this equation. It tells you, take the thing corresponding to the first coordinate to the third power and subtract the thing corresponding to the second coordinate to second power. Yeah? So, in fact, this is one of the characterizations of toric varieties. They are prime ideals generated by binomials. So, by binomial, when I say a binomial, I always mean xi minus xb. This is a binomial for me. So there's also a paper, Eisenbach-Sturmfell's binomial ideals, and they mean something different. There is a lambda here, but when I say a binomial, I always mean like this. And a binomial ideal is an ideal generated by binomials. So it turns out that for toric varieties, every binomial comes from an integral relation among lattice points, and these binomials span even as a vector space, the whole ideal. Okay. So we know already a lot about toric varieties. Now we have to learn about normal toric varieties. Normality is a very nice condition, but even nicer is projective normality. So let's define X in Pn is projectively normal if the affine cone is normal. And this condition of projective normality translates in a very nice way how these lattice points in a lattice have to look like. So maybe first a remark. It's not true, even if your variety is smooth, that these points have to form a convex set or a polytope. So it may happen that these points do not form, they have like a hole inside, but your variety is even smooth, a smooth projective variety. But the cone over it will not be normal. So you can restate that a projective toric variety, so let's take X projectively normal toric variety, and then the condition is equivalent to the fact that, and I will first write it and then I will explain it, that A0 up to AM is a normal polytope. And I should say in the lattice it spans. So first of all, let's look at the brackets. If you pick lattice points, they do not have to generate as a lattice the whole lattice. For example, if you pick some even numbers, no matter how you add them and subtract them, you will not get odd numbers. Yeah? So you always, when you are doing toric geometry, you should work in the lattice that your points generate. That's, by the way, a theorem that this will always be a lattice. You will not get some other group. And when I say a lattice, I always mean z to some power. Yes? So you always assume that your points span the correct lattice. Now I should say, what do I mean by a polytope? I mean a polytope, it's a convex hull of a finite set of points. But what do I mean that a finite set of points is a convex hull? I mean, these are like continuous objects. So when I say this, first of all, when I mean a polytope, I always mean an intersection of a polytope with a lattice. Yes, so by this I mean that these points, these are all lattice points of a convex hull of some lattice points. Yes, so an example, if we take, well, there were already some examples given by Greg. If you take all of these points here, yeah, these are all lattice points in a convex hull of those 3 points. But if you take these points, this is not a polytope because you are missing a point in the convex hull. Okay? And there is one more thing, normal. Yes? So normal, so a lattice polytope P is normal even only if every point for every k, and for every k a natural number, and for every point in the kth dilation of P, we have P is equal, let's intersect it with the lattice. So I will call the lattice M. Wherever we work. Okay, we intersect with M, and then P is a sum of P1 plus pk for I in the polytope lattice points. So in other words, each pi has to be one of those. And that's the definition of a normal polytope. And this is a theorem. So you might be surprised. How could it be that you have a polytope, you take a cave dilation, you take a lattice point, and why is it a sum of k lattice point? I mean, it seems that it should be always true, but it's not always true. And in high dimension, it's even a very restrictive property for the polytope. But it allows you to somehow measure the singularities. Because once you have a normal toric variety, a lot of things automatically follow. Like, for example, it has rational singularities. In particular, it's Cohen-Macaulay. So it's a very strong condition, normality. And in fact, if you look at some standard books, usually when people define toric varieties, they define them to be normal. For example, because of this condition and because they want to work with a fan, but this I don't plan to mention. And this theorem is a consequence of a similar theorem for affine toric varieties. So when is an affine toric variety normal? Theorem. So A1 up to AM defines a normal affine toric variety, even only if the monoid generated by these lattice points monoid. Okay, so maybe it sounds scary, but I just mean you add them. Yeah, you add them. Yeah, and this is the monoid generated by the lattice points. And this has to be equal to the cone, to a cone in a lattice they span. Okay, and what do I mean by a cone? Well, Greg was already talking a lot about cones, but I mean always polyhedral cones. So for me, a cone is just like a finite number. Oh, and I will also work only with rational things. So I will take a finite number of integral linear forms, and I declare that the cone says that it's a system of linear integral inequalities. Okay, so for example, if you take 2 and 3, you remember our favorite example, what's the monoid generated? Well, you can add 2s and 3s. So for example, if you add 2 and 2, you will get a 4. If you add 2 and 3, you will get a 5. So you will get everything up. Yes? But this is not a cone, because no matter how you add 2 and 3, you will never get a 1. And there is no way of defining positive numbers without a 1 as inequalities. Yeah? You would have to add this 1 to have a cone. And this whole is exactly the reason why the cusp is a non-normal affine toric variety. Perfect. Let's go back to Greg's lecture, and let's go back to Veronese. So Greg wrote the second Veronese of P2, yes, and this was given by monomials, yes. So it was like x squared, y squared, z squared. Okay, so what are these? Well, let's write it: y squared, z squared, xy, xz, yz. Well, again, we look at exponents. So this is like a point 2, 0, 0. This is a point 0, 2, 0. 0, 0, 2, 1, 1, 0, 1, 0, 1, 0, 1, 1. Yeah? And you can see what you will get. You will get twice a simplex. Yeah, so this is 2, 0, 0, this is 0, 2, 0, this is 0, 0, 2, this one is 0, 1, 1. Yeah? So in toric geometry, we do not think about the image of this map, we think about such a twice the unit simplex. You can read off a lot of things from this picture, more than you can imagine. For example, if you are interested, what is the degree of V2 of P2? Well, it's the number of unit. It's the normalized volume. So in other words, you can divide it into 4 unit triangles, and it means that the degree is 4. You can also read off a lot of defining equations. For example, this point plus this point is twice this point. This will give you a defining quadric of the Veronese surface. Okay. Now a little bit more generally, let us consider the Rth Veronese of Pn. Okay, this goes. This takes all monomials in n plus 1 variables of degree r. So let's see if I can compute how many are such things. Well, we need to do something like this. And if I made a mistake, please correct me. Okay. So a question for you: how would you describe the corresponding polytope? So here it was an example for r equal n equal 2. So think first, what when r is equal to 1? Well, this is then just an identity map that takes all monomials of degree 1. So in other words, it just takes, well, what's a monomial of degree 1? It's a variable. So it's as an exponent, it's like 0, 0, 0, 1, 0, 0, 0. So it's a basis vector. Yeah. So when r is equal to 1, you are getting the unit simplex. Yeah. Okay. So Pn corresponds to a simplex. So let's call it delta. Now, what will be the Rth Veronese? I didn't hear. Really? Well, so now we have an Rth Veronese of Pn. So these are now all monomials in n plus 1 variables of degree r. So we need to take all exponents of all monomials in n plus 1 variables of degree r. So in other words, we are looking for integral points that sum up to r and are non-negative. Yeah, so maybe you can see that this is r times this simplex. Yeah? If you rescale it r times, you will get this. And one more thing that I wanted to present that did not appear in Greg's talk, but I think it's very nice. It's the Segre embedding. Oh no! No, it's what? A1 plus 1 times a k plus 1 minus 1. Okay. And what happens here? Here you take all monomials of degree k that are, maybe I will write it, all monomials of degree k that are of degree 1 with respect to each p ia. Yeah? So you pick a variable here, pick a variable here, pick a variable here, pick a variable here, and you multiply them. Yeah? Okay, so how can we look at it? Well, we already know that this is a simplex. This is a simplex, this is a simplex. And lattice points of this simplex, they correspond to variables. So in other words, choosing a variable here, a variable here, a variable here is like choosing a lattice point here, choosing a lattice point here, and choosing a lattice point here. So we are looking for a polytope that parameterizes all choices. A lattice point here, a lattice point here, a lattice point here. So let's call this n. And now you can see that this is just the product of the polytopes. Yeah? Okay, so I already told you some properties like the degree, how to check the normality. Maybe the most basic that I should have started with is the dimension. The dimension of the toric variety always equals the dimension of the associated polytope. So, for example, reading of the dimension is very easy. And the last property that I wanted just to tell you is that you can read of the singular locus from this description. And how do you do that? Well, the most singular points, so yes, I didn't mention it, but the points in the torus, the vertices of the polytope, they correspond to torus invariant points of the toric variety. I didn't mention the torus action so far, but if you have, for example, a projective space, you know the torus. These are the non-zero points. And you also know the torus invariant points. These are like 0, 0, 0, non-zero, 0, 0, 0. These are the only torus invariant points. And they, we already said, they correspond to like vertices of the simplex. So this story generalizes. The vertices of a polytope, they give you torus invariant points of the toric variety. And how do you see if this is a singular or a smooth point? You do the following. So you have a vertex of a polytope. So you look at it, and what can you see? Well, you see some edges going from this polytope. Yes? And okay, so polytope P defines a smooth projective toric variety if and only if for every vertex of P we have two conditions. I will write it here. We have two conditions. Well, first of all, there are let's say that this is of dimension n. First of all, there are n edges of P adjacent to V. Let's call them E1 up to En. Yeah, so they start at V and they go somewhere. And the second of all, if you look at first lattice points on those edges, so on each edge it goes and it has some lattice points on it. So let's say that let Vi be let Vi in EI be a lattice point nearest to nearest to V. Yeah? And the condition is that V minus Vi is a basis of a lattice. Okay, maybe it sounds complicated, but let's do an example and let's see it's trivial. Let's take such a toric variety. It's a square. It will correspond to P1 times P1 that you already know, because this is a simplex and this is a simplex and this is a product of simplices. So in particular, it should be smooth. So what do we have to choose? We have to fix a vertex. So this is V. We need to take edges adjacent to it. There are two of them, so at least the first condition is satisfied. Then we have to look at the first lattice points that we encounter along the edges. These are the v1 and v2. And then we need to subtract v1 minus v and v2 minus v. So we are getting these vectors. And we have to check that they form a lattice basis. Well, clearly they do. OK. So that was the toric part. Now we all know toric geometry. And now we are going to learn about secant varieties. So I already gave 2 lectures on secant varieties, or maybe even 3 in Korea. But let me just recall the definition that if we have an X in the projective space, then we define the kth secant variety of X as the union of projective spans of k points, where x1 up to xk are points of X, and we close it. Yes. And the particularly interesting case for us will be the second secant variety. Now, why do we have to close it? It might be surprising a little why it looks like if we are taking points in the linear spans of k points, the limiting point should also be on the linear span of the limit of those k points. But the thing is that points may start crashing together. Even if you have 2 points, which means that you have a point on a secant line, if you start moving it, you may lie not on a secant line, but on a tangent line. That's why we also define a tangential variety. And I will only define it under the assumption that X is smooth. And here it will be just the union of all embedded tangent spaces at all points of X. Okay. Now, I introduced you the Veronese and the Segre variety. And this is just R times the simplex, and this is just a product of simplices. Very easy, nice toric varieties, smooth, projectively normal. They have quadratic Grubner bases. They are arithmetically Cohen-Macaulay. They have rational singularities, and so on and so on. They are defined by quadrics, binomial quadrics. What about their secant varieties? Well, it turns out that secant varieties, even the second secant varieties, is already a much more complicated object. It's not smooth. Not only it's not defined by quadrics, but there are no quadrics that vanish on it. In fact, it was an open conjecture proved by Claudiu Raicu that this is defined by certain special degree 3 equations in case of Segre-Veronese varieties. But already that was a difficult problem. And now comes the trick. So, maybe for those of you who know Segre-Veronese varieties, which is a generalization of Veronese and the Segre, that will be easy. For those of you who don't know, there is a combination. So instead of taking R times 1 simplex, or a product of simplices, you can embed the product of projective spaces by higher very ample line bundles. And in other words, you can consider A1 delta N1, let's using the previous notation, times RK delta AK. You can consider such a polytope, and this is called, the corresponding variety is called Segre-Veronese. But you can focus on Segre or Veronese as you wish. Few words about dimension and when they coincide. So, how would you expect the dimension of the second secant variety? What would you expect it to be? Well, we have to choose a point on the variety. We need to choose another point on a variety. And we need to take a line through them. So in particular, the dimension is always at most twice the dimension of X plus 1. 2 for choosing 2 points and 1 for the line. But in fact, it can be smaller. But there is a theorem of Zak. I maybe will not state it. It's here in Korea. I gave a complete proof last time I was here that this of smaller dimension, even only if these two varieties coincide. That's a famous theorem. Okay, and now let's go. So the rest of the talk will be based on a joint work with Oding and Zwiernik, and with Sus and Perpeczko. The article appeared just yesterday on Archive, especially on this occasion. Okay, so what's the theorem? So I'm claiming that this complicated variety, such that you cannot say what are its defining equations easily, or this one, that in fact they can be represented by a polytope. And I even claim they can be represented by the same polytope as the Segre-Veronese. There is only one more equality that you need to add to this polytope. So now we will be getting more and more precise with this statement. First of all, we choose a vertex here. We choose one vertex of this polytope, and we assume that it's 0. This corresponds to, as you already know, to choosing an affine space in this projective space. Yes, so choosing one vertex is like choosing an affine space. And the theorem is as follows. So let's say that this is in Pn, and X is Segre-Veronese. This is a toric variety. And the same thing with this. Yeah. So in other words, you can read off all of the properties like singularities, dimension, whatever you like, type of singularities, even Zach's theorem, just from a polytope. Yeah? Because it's a product of an affine space and a cone over a projective normal toric variety. Well, if it's a projectively normal toric variety, it means that there is an associated normal polytope. So what's the polytope? It's the same one as this one. It's exactly the same one. So this, let's say it lives in some lattice ZS. And you only add one more equation. And the equation is sum of, well, I have to somehow name the basis here. Let's call it EI. Yeah? So something very, very, very easy. Yeah? Okay. Now, what about this one? This one does not have to be normal. This one does not have to be normal because well, for example, for the Veronese, you can easily see that sometimes the singular locus is too big. And we will be looking at the singular locus in a second. But again, it's an affine toric variety. So it needs to correspond to a set of lattice points. Yeah? So what are the lattice points? And now a funny thing, the same as here, intersected with this inequality. Exactly the same lattice points. It's just that once you consider them as a polytope, so you put them at height 1. So in other words, you sort of look at an affine cone over homogenization of these things. And for the tangential variety, you just consider them as monomials. You just take a map using those points. So let's look at some examples. Okay, so the first one is P1 times P1 times P1. So P1 corresponds to a segment. Yes? So P1 times P1 times P1 corresponds to a unit segment times a unit segment times a unit segment. So it's a three-dimensional cube. Okay. Now, what happens when we cut with this? What do we get? Yeah, you have to imagine a three-dimensional cube cut with sum of coordinates greater or equal than 2. So the cube has 8 points. How many points we will have left? I will give you 1 point that will be left. A point 1, 1, 1. It has certainly sum of coordinates greater or equal than 2. Anything else?
0, 1, 1.
0, 1, 1. Okay, if we have 0, 1, 1, you can probably guess the two others. 1, 1, 0. Okay, and these are all. I mean, these are all lattice points that will be there. And this is a simplex. Yeah, this is a simplex, which means that it represents the projective space. So it means that the cone over it is the whole affine space. So it means that the product of an affine space and an affine space will be just the whole affine space. And this is in fact the case because here the secant variety fills the whole ambient space. But what about the tangential variety? Well, for the tangential variety, we need to look at the image of these monomials, of this monomial map. And there is an integral relation among them, namely this plus this plus this is equal to twice this point. Yeah? Which means that our tangential variety will be given by such an inhomogeneous equation. Yeah? So from this you already read that the tangential variety of this thing is a hypersurface, which locally on an affine piece is given by such a very simple equation. Let's do one more example. I wanted to do the Veronas surface. Okay. This is an interesting one. Okay, so this is the point 0, 0. You already know. This is a 2, 0, and this is a 0, 2. Yeah? So I take the previous polytope, but I need to shift it so that 0 is one of the vertices. I always need to do that. Okay, now what will happen when I intersect with this? What happens? Yeah, I'm getting this. Yes. So I'm only getting a segment. Yes? Okay, so this is a segment. And what can we deduce from this? Well, we can deduce from this that these monomials, they are homogeneous. So it doesn't matter if you take a map to the projective space by them or to an affine space. Yes? They are the same. Yeah? It doesn't matter if you take a map x square, xy, y square, or if you take a map T, T, T. That's already a cone. So it means that in this case, these two varieties, they coincide. Yeah? And you can see it. You can see Zach's theorem here. These two varieties will coincide if and only if these monomials will lie on a hyperplane cut. But on the other hand, they will rely on this hyperplane if and only if the intersection is of smaller dimension. Yeah, so this proves Zach's theorem for Segre-Veronese. If you are losing dimension, it means that the polytope you are getting has to be contained inside of the cut, which means that all of your relations will be homogeneous. So the tangential variety has to agree with the secant variety. You can also see that there is an equation here, y squared minus xz, of the secant variety of the second Veronese of P2. So what is this equation? What is this equation? Well, the second Veronese represents rank 1 3x3 symmetric matrices. These are rank 1 symmetric 3x3 matrices. So this is a sum of two rank 1 symmetric 3x3 matrices. So these are rank 2 symmetric 3x3 matrices. So what's the equation? It's the determinant. Yeah? So it's really a hypersurface. And now you should say, oh, come on, the determinant of 3x3 matrices is of degree 3. And I gave you a degree 2 thing. But still, it's completely fine. The thing is that we are working in an affine space, and to prove this theorem, we are using non-linear changes of coordinates, higher degree automorphisms of an affine space. And in particular, these automorphisms, they transform the degree 3 equation of this variety into such a simple binomial quadric. Even more, if you take any Segre product, it will always be true. So this variety will have this nice property that it's defined by a degree 2 quadratic Grubner basis. That's one of the strongest properties a toric variety can have. A degree 2 quadratic Grubner basis. It implies such things as normality, as unimodular covering, in particular Cohen-Macaulay singularities, in particular rational singularities. A lot of these properties follow. But what about the toric variety? Well, for the toric variety, you can immediately see that for the tangential variety, that this does not have to be normal. In particular, let's take the third Veronese. This is something that I didn't know. I learned it only quite recently. So this is the third Veronese. And if we look at the tangential variety, we are left with this. Yes? But now we have to span a monoid with this. Well, this is not a normal thing. Of course it's not a normal thing, because it's not a cone, because we will never get these points. Yes? So if you look at this as a polytope, it's fine. But if you look at it as a tangential variety, as lattice points in a lattice, non-homogeneous thing, it's not normal. Okay. I still have 5 minutes, so I will give you some things that one can do with it. So one thing is one can classify Gorenstein. The problem with Gorenstein is that no one knows how to pronounce it. Of P A1 times PAK. So when k is equal to 2, there is a classical theorem that this is Gorenstein even only if a1 is equal to a2, even for higher secants. But it turns out that there are just a few other examples, namely k equal to 5 and all ai's equal to 1. And the other thing is like 3, 3, 3. So I mean k equal to 3 and a1, a2, a3 equal to this. Then there is a 3, 3, 1. And then there is a 1, 1, 3. And there is an open problem here. So when I write Gorenstein of a projective variety, I mean that a local ring for any point in the projective space is Gorenstein, because my method works only on the affine space. But in neither of the works, neither with Piotr and Luke or with Alexander and Hendrik, we cannot prove that the affine cone is Gorenstein in those cases. I think in this case it's known, but in those cases we don't know. So the classification of arithmetically Gorenstein secants, it's still like in front of us and of everyone. So it's an open problem hidden here, to classify arithmetically Gorenstein secants of Segre maps. I should say that first results of this type appeared in a work of Sturmfels and Zwiernik for the tangential variety of a product of P1s. I should also say that the technique to prove it is based on moments that Gregory was talking about, but not so much moments, but their relations to another object called cumulants in statistics. So the relation between moments and cumulants is exactly the automorphism that we need to prove this theorem. But I should say also that moments and cumulants, they come in a zoo. So it's not that if you know that you should use moments and cumulants, you will prove it easily. You need to know what kind of cumulants, what kind of moments, and this is described in our work. I wanted to prove some other thing. Do you know what is the singular locus of the secant variety? Does anybody know? I didn't hear. Be brave. Say.
Next secant variety. Third secant variety.
No. The third secant variety contains it, so it's bigger. So the previous one, yeah. Yeah. So that's what I think quite a few people thought. So the underlying variety is always contained in the singular locus, but it's not. The singular locus is bigger. And in general, what you have to do is you have to take two projective spaces, and you need to take their secant variety, and you need to product with all the other projective spaces. So in particular, there are k choose 2 components. And this is a general thing. There are a few exceptions. Again, a finite list when the singular locus is a little different. And you can see it. You can see it on this picture. So you have to take a product of simplices, and you need to cut it with this half space. And what will be the singularities? For example, imagine a 4-dimensional cube, a 4-dimensional unit cube, cut it with this. What will be the singular points? Well, they will be like this. So 2 1s and all the other things equal to 0. And they exactly encode these components. That's the reason why we have k choose 2 from the toric point of view. Again, we are getting that these varieties are normal. Cohen-Macaulay in particular have rational singularities. And just for the last 30 seconds, one more property that I like and that people study, but I don't think that algebraic geometers dealing with such things, they know it a lot. It's called flexibility. And flexibility is is the property of transitive action of a special automorphism group on the smooth locus of a variety. But let me just give you one of the corollaries of flexibility. So it turns out that if you take a cone over any Segre Veronese, and an affine cone over it, if you take any number of points, P1 up to P100, in the smooth locus, smooth points, smooth, and if you take another 100 smooth points, there exists an automorphism of this variety that takes these points to these points, no matter how many you take. That's one of the properties of flexibility. And people study it usually in affine algebraic geometry in relation to affine spaces. So that's one of the invariants to distinguish a variety from an affine space. Thank you very much.